continue our discussion on the frequency response of the amplifier. We have seen that there are 3 factors which may result in 3 different values of lower cutoff, but in the graph when we plot frequency versus gain, then we get actually just one lower cutoff, which is f1. Now, 3 factors may contribute to the lower cutoff. One arises from the first coupling capacitor at the input. The other cutoff may come from the second cutoff at the from the second capacitor at the output, and similarly bypass capacitor, which we use with Re to enhance the gain, that may also give the third cutoff. But as in the plot we get only one value f1. So, which of these 3 f1, f1 prime, f1 double prime we have to consider? The one which is out of these 3 which is having highest value of cutoff, higher value of frequency, that will be the one with that we call f1. Similarly, we discussed that for the upper cutoff, upper cutoff, the coupling capacitors and bypass capacitors are not responsible, they have no role to play. Beyond these frequencies, they behave like a short. So, why the gain falls at higher frequencies, and as said in the beginning that this fall occurs because of the contributions of junction capacitances. Now, junction capacitances, we have seen that the analysis will require the use of Miller's theorem. Miller's theorem is the one which we use to reduce the impedance whose one end is connected at input and other end connected at the output to its equivalent value at the input terminals and the equivalent value at the output terminals. These are given by Miller's theorem, and we have seen that for example, the junction capacitance between collector and base, that is the situation suitable for the application of the Miller's theorem. And so, at the input the Miller equivalent of this capacitance is multiplied by the gain, and gain is quite high. We are talking about, for example, for common emitter amplifier in which the gain is 100, 80, 200. So, a small capacitance gets magnified to 200 times or 100 times, 150 times, and it is responsible to give you the upper cutoff. So, this is one capacitance. Similarly, at the output there is the effective equivalent capacitance from by using Miller's theorem we get, that may give another cutoff. And third cutoff we were talking that comes because the current gain beta, which is the ratio of IC, the collector current, output current, to input current, that is base current, and this falls at very high frequencies, and this fall we can express in terms of the value f t, which is the gain at which the frequency at which the gain falls to unity, which is provided by the manufacturer. And out of these 3, whichever has the lowest of the upper cutoff, that is the frequency f 2 here that we get in the plot. So, having said this, now we should see how multi-stage amplifiers will behave. So, we take next the multi-stage. multi-stage amplifiers. We have been considering so far single stage amplifiers, that means one transistor with its biasing network and coupling networks, that forms a single stage amplifier. The gain of the single stage amplifier may not be sufficient for many applications, whether the application includes a running of a motor or some other equipment, that may not be sufficient. In practice, actually single stage amplifiers are having less use. Multi-stage amplifiers are used. What is multi-stage amplifier? A amplifier in which more than one stage, it may be 2, 3, 4, they may be identical or different type of stages, they are joined together, they are connected normally in series, and so this is also known as cascade amplifier. So, multi-stage amplifier or cascade amplifier we have when more than one amplifying circuits are connected. Like we take for simplicity a two-stage amplifier, which is a multi-stage amplifier, and we talk about the salient features of this. So, here there are two amplifiers. This is amplifier 1, having voltage gain A V 1. This is amplifier 2, having gain A V 2. This is the input, and this is the net output V out. Now, 1 and 2 I am writing, this is the input to the first amplifier, and this is the output from the compound amplifier. Now, here the output, this output here is V out 1 from the first amplifier, whatever is the output, that is here, and this is the, here we feed what is known V in 2, and obviously the output, because the output of the first amplifier is fed to the input to the next amplifier. So, obviously V out 1 is equal to V in 2. The output of first stage is equal to the input to the next stage. Now, in this two cascaded stages, what is most important? There are few things which are most important. One is, what is the overall gain? If the individual stages, individually amplifier 1 has a voltage gain A V 1 and amplifier 2 has a voltage gain A V 2. Then what is the net voltage gain in this amplifier? This is A V, voltage gain of 1 and 2 combined. That is why I have written the gain as 1 2, and this is obviously, look at this circuit, the gain, the input here is V in 1 and output is V out 2. So, obviously, the gain is output voltage to the input voltage. So, here it is V out 2 V in 1, and this can be written in the form V out 1 V in 1 into V out 2 and V in 2, but this is equal to, we have seen that V in 2 is equal to V out 1. So, this is further V out 1 V in 1 and this is V out 2 and V in 2, because V out 2 V out 1, because V here V out 1 is equal to V in 2. So, V in 2 I have written as V out 1. So, this cancels out and we are left with what we have written V out 2 by V in 1, and this is therefore, for the compound amplifier the gain is, this is A V 1 and this is A V 2, very important relation. The what if individually the two amplifiers are coupled, are cascaded, having the individual values of the gain A V 1 and A V 2, then what is the value of the net gain, that is the product of the two gain. Remember, product of the two gains. Let us take an example that in a two stage amplifier, let A B 1 be equal to 20 and A V 2 be equal to 30. They may be identical or they may be different. So, I have taken 20 and 30, then gain of the two stage amplifier, gain of two stage, that is multi stage amplifier, that is the product of the two. So, 20 into 30, this is 600, it is the product. If we feed here 1 millivolt, this will appear at the output of 600 millivolts if the gains of individual stages are 20 and 30. So, it is a big gain. Now, we have talked about decibel scale, dB scale. When gains are expressed in dBs, then for multi-stage amplifier, the dBs are additive, because dB is a log scale. So, the product becomes a addition in logarithmic algebra. So, therefore, we can write, when we talk of voltage gains, then in dBs we can express 20 log 10 V out 2 V in 1, and this is equal to 20 log base 10, and here V out I am writing in brief VO 1, V in I 1 into V out 2 and V in 2, and this can be written as 20 log base 10 AV1 into AV2, which is A12, that is gain of the multi-stage amplifier in dBs. This is AV1 in dBs plus AV2 in dBs, additive. And we are for simplicity considering only 2 stages. Actually there can be many stages. So, for example, if 3 amplifiers having gain of 20 dB each, then for 3 stages of the multi-stage amplifier, gain will be gain for 3 stages will be 20 dB plus 20 dB plus 20 dB. For 3 stages gain will be 60 dB. So, while the gains when not expressed in dBs, they are product, but once they are expressed in dBs, they are additive. So, this is about gains. I repeat that gains are the product of individual gains, and when the gains are expressed in dBs, then they are additive. This is about the gain may be voltage gain, current gain, anything, or power gain. Now, and we can extend it to any number. 2 stages we are considering, 3, 4, 5, n number of stages, the same rules are applicable. Now, what about the phases? These are algebraically additive. These are, by simple intuition we can see that they have to be, these are additive. So, if we couple 2 amplifiers, for example, both have a phase difference of pi, then if there are only 2 stages, then pi plus pi. So, the phase difference will be 2 pi, that means output will be in phase with the input. So, phases are additive, and if one has a phase of pi, other has a phase of minus pi, then 0 phase will appear and so on. So, phases are additive. Now, so these are 2 important considerations about multi-stage amplifiers, how the voltage gain or current gain. So, in general how gains are related with the individual values. So, they are normally products, and when expressed in dBs they are additive, and phases they are additive algebraically. Now, frequency response. Frequency response of multi-stage amplifier. Frequency response of multi-stage amplifier. It is now very clear that by adding stages we amplify the signals much more and gains go very high. If you remember, we have said that gain and bandwidth product is constant. This is constant for an individual circuit, this is constant for a system. System means multi-stage amplifier. So, when the gain goes high, the bandwidth has to fall. So, remember that in multi-stage amplifiers the gain the gain increases, bandwidth falls. Now, numerically we have to calculate this fall in bandwidth. The calculation of bandwidth of the multi-stage amplifier is not difficult in two cases, and the two cases are case 1 when stages which have identical lower cutoff and upper cutoff, when they are coupled, when they form the cascade amplifier, the multi-stage amplifier, then the calculation is simple. And I repeat what I am saying. Suppose we connect two amplifiers, they have identical lower cutoff and or identical out of the upper cutoff, then it is very easy to calculate the cutoff lower as well as for upper for the multi-stage amplifier, and the expressions are. So, the case 1 is stages having same closely equal lower and or upper cutoff frequencies. If for example, lower cutoff is the same, uppers they are different, then this calculation in case 1 what we are talking will be valid only for the upper for the lower cutoff which are identical, and if only upper is identical, then the rule which I am just putting here, that will be applicable to the upper cutoff, and if both are identical, then these both expressions can be used. So, if n stages are cascaded, then the lower cutoff for the system, that means for the multi-stage amplifier, this is F1 is the cutoff for the individual stage, then this is 2 to the power 1 by n minus 1, and F2 of the system is equal to F2 by 2 to the power 1 by n minus 1. This is the expression F for lower cutoff, upper cutoff of a multi-stage amplifier if they have same lower cutoffs and higher cutoffs. If only one is identical, then only corresponding expression is to be used. We can see that how the lower cutoff is increased and upper cutoff falls. Here the gain, if this is F1, this is F2, if this falls, then we are talking about something of this kind. It has fallen and this increases. So, Earlier bandwidth was this one, and now the bandwidth will be a reduced one. We take an example. Let f1, that means the lower cutoff for the individual amplifier is 20 hertz, and upper cutoff is 20 kilohertz. The bandwidth is f2 minus f1, which is 20 kilohertz minus 20 hertz. 20 hertz is negligible in comparison to 20 kilohertz. So, this is simply 20 kilohertz. This is the bandwidth of the individual amplifier. Now, suppose two stages are cascaded, then f1 for the two stage amplifier from this expression 1 by n becomes equal to 1 by 2, because n is equal to n is number of stages, n is number of stages. So, that gives 1.55 f1, that is 1.55 into 20 hertz, and it comes out to be 31 hertz. Lower cutoff increases from 20 hertz to 31 hertz when two stages are joined together to form a multi-stage, and the upper cutoff f2 prime two stage amplifier, this is 0.64 f2 from this expression 2 to the power half minus 1, when you solve it, it comes 0.64. So, that this is reduced from 20 kilohertz to 12.8 kilohertz, and because 31 is very small. So, bandwidth for this two stage amplifier actually is reduced from 20 to 12.8 kilohertz. So, if more stages identical, even this stage if you solve for 4, this will be much reduced, bandwidth falls, and the physical reasoning we can get from the fact that gain bandwidth product is constant. So, we have seen numerically that while the gains are enhanced drastically, but the bandwidths fall. So, in a multi-stage amplifier, to maintain a reasonable bandwidth even for the multi-stage amplifier, we have to start with individual stages which should have much higher bandwidth than required in the application. How multi-stage amplifiers are obtained? What are the methods of coupling, either stages or even how we couple a signal source to the amplifier. There are three methods. Methods of coupling. Methods of coupling. There are three methods. One is RC coupling, other is direct coupling, third is transformer coupling. these are the three methods which can be used to couple either various stages of amplifiers, or at the input the source can be coupled to the amplifier by any of these three methods, and similarly at the final stage the load can be a loudspeaker, a printing machine, or some other gadget that can be the power can be coupled by any of these three methods. We discuss one by one. RC coupled, this is what we have been discussing, the lower cutoff, upper cutoff we have said, and that was the RC coupled amplifier, when we take a source here and we source resistance RS, and this was the capacitor, and we have derived the expressions also for it, that was RC coupling. RC coupling is very widely used because it is most convenient, it is integrable, but only difficulty is, as we have seen in our studies, that it puts a restriction on the lowest frequencies which can be amplified. The graph for a RC coupled amplifier, gain versus frequency goes like this. So, this is the lower cutoff. So, for example, 0 frequency DC signals cannot be coupled by RC coupling, the signal will not go to the next stage. So, anyway we have discussed enough the all analysis of the RC coupled circuits that we have discussed, and now we take another method of coupling, which is direct coupling. In direct coupling, the signal is coupled, just it is connected by a conductor. For example, in direct coupling, if this is the signal source or the previous stage, it is just coupled to the base of the next. Direct coupling, there is no capacitor involved in it. This is also quite in recent years, say last 20 or 25 years, this coupling has found big applications, and for example, in operational amplifiers, op amps, which we are going to study in details in later modules. So, op amps, most of the op amps make use of direct coupling. There I said, if you remember, that op amp is a multi-stage amplifier, and there are several stages which are directly coupled. So, there will not be any restriction on the lower cutoff when this is connected directly, even if it is a DC signal, it will be able to propagate, to couple. So, the response for direct coupled will have no cutoff, lower cutoff, no, but upper cutoff, for which this is gain, this is frequency, there is no lower cutoff, we start from 0 frequency, still the gain will be there, and the upper cutoff falls, if you remember, because of the junction capacitances, and whether we are using a bipolar transistor or a FET, this is always there. So, this cutoff will be there, this will be there. So, in direct coupling, in ICs and in operation amplifier is also in IC form. So, integrated circuits and op amps etc., they make use of direct coupling. So, while the biggest advantage, there are two advantages, there is no need of capacitor. So, capacitor formation in IC will not be required. Other thing is, there is no limit on the lower frequency, right from DC to higher frequencies you can couple. Of course, the higher fall at very high frequencies beyond mid band, the cutoff will be there, and that is because of the junction capacitances. Now, there is one disadvantage with the direct coupling, that the disadvantages rather, one is not very serious, though it is a disadvantage. When we couple these stages directly, then even DC are coupled. If we put RC coupling, then we have seen that the capacitor isolates one stage with the other. Capacitor acts as a block for DC. So, we can design the amplifiers more accurately individually, and then we can use RC coupling, and because for DC purposes the capacitors will keep them isolated. So, the biasing etc. are not affected, the Q points, the operating points are not affected. But when we use direct coupling, then we are connecting them for direct voltages also, DC voltages also, and hence the design has to be done more carefully. But more serious than this, we will take a design example to illustrate it what I have just said. And more serious than this is that low frequency noise also gets amplified, because that capacitor will block it, capacitor will block this low frequency noise. Here in direct coupling there is no blockage, there is no restriction on the frequency. So, even noises will propagate through the amplifier and they will be amplified. Now, this problem can be taken care of by taking more advanced circuits like differential amplifiers, where we can filter out these noises by a different mechanism that we will see when we talk of differential and operational amplifiers. Let us take, so direct coupling is nothing, simply a connector connects the sample the signal or the output from the last stage to the load directly by a connecting wire. If it is individual, I mean if it is discrete amplifier, then a connecting wire, otherwise a conducting path on the IC will do the direct coupling. We take a design example. Let us consider this circuit. This is a direct coupled two stage amplifier. I take just one design example. This is plus 12 volts and there are two transistors which are directly coupled, and let us say that base of transistor Q1 initially is at plus 2.1 volts, that is 2.1 volt is available here, and these resistances are given. This is 700 ohms and this is 3.3 kilo ohms. This is 4K, and what is given is that for both these transistor Q1 and Q2 the current gains are same, beta is 100 each, and the voltage drop, this drop here, this is 0.7 volts here and this is also 0.7 volts here. So, VBE as we call it, this is 0.7 volt. So, the problem now is that what should be the value of RC to put the collector at plus 5 volts. We have to find out the value of this resistor. Now, the solution I give: the emitter current in Q1. So, I E1 for Q1, this you know now what we have done earlier in our earlier module, that how to calculate this voltage minus this divided by this will give you the IE. So, IE1 of Q1 is VBB minus VBE divided by RE1, and this is 2.1 volts minus 0.7 volts by 700 ohms, and this gives 2 milliampere. And so, this 2 milliampere IC and I, they are the same. IC always in transistor, bipolar transistor analysis is equal to IE. So, 2 millimeters flows through here, then we know how much will be at what voltage base of Q2 will be. And let us put this point A here. What is point A? That is the same, the potential here will be the same as the collector of Q1 or base of Q2. So, here VA will be simply Kirchhoff's voltage law you apply, 12 volts here, this is connected to 12 volts and 2 milliampere current is flowing. So, obviously 4K into 2 milliampere current is flowing through that. So, this is 8, and so this is 12 minus 8 is equal to 4 volts. So, the potential here is 4 volts. 4 volts, now we proceed in the same way here. Out of 4 volts, 0.7 volt drops across this junction, which I write the I2 IE2, this is for Q2, this will be equal to 4 volts minus 0.7 volts divided by RE. So, 4 volts minus 0.7 volts divided by RE is 3.3 K, and this is also 3.3 volts. So, 3.3 volts divided by 3.3 K gives 1 milliampere, 1 milliampere current. This is same as IC 2 here. This current is flowing through this resistor. With this we have to find out, and again we apply, remembering that this is to be maintained at 5 volts. Then RC we can find out like this, that 12 volts, out of that 5 volt is the requirement that the collector should be at 5 volts. And what is the drop here? IC into RC. So, plus RC into IC, and IC we have found out to be 1 milliampere, and from here we can find RC, and that comes out to be 12 minus 5 volts divided by IE, which is 7 volts, 1 milliampere. So, this is 7 kilo ohms. So, we have to use a resistance of 7 kilo ohms to get the voltage at 5 volts. So, this is the design principle I have illustrated through this example. Now, one of the very popular direct coupled multi-stage circuit is what is known as Darlington pair. Darlington pair is a two stage amplifier where two transistors are actually directly coupled. The circuit is this. This is sold in the market as a single device. This is all enclosed. These are two transistors Q1 and Q2. This is Q1, this is Q2, and this is base, this is collector, and this is emitter. And here the current IB1 flows, and this is IC1, this is IE, which is same as IC1, and the same current becomes IB2, and here it is IC2. As I said, this is enclosed as in a single packaging, and the three leads like a transistor, they are available. And what is the use of why we are doing this? Voltage gain we have seen. Now, this is the example of current gain, that if the current gain for Q1 is beta 1 and current gain for 2 is beta 2, then for this Darlington pair the current gain beta will be the product of the two, and this we can very simply see that what will be if the input current is IB1, what will be this current IC1, you know it is beta 1 times IB1, and IB1, this is IB2 is same as IC1. This current is the same as this current, and this current is going on. So, IB2 is equal to IC1, and then IC2 is beta 2 times IB2, and IB2 is simply IB2 is same as here, this is same as IB2, this we substitute in this. So, IC2 becomes beta 1 beta 2 into IB1, and what is the current gain? The current overall current gain beta, which is the ratio of output current to input current. Now, for the collective composite direct coupled amplifier, output current is IC2, input current is IB1, and from here we find that this is the beta 1 into beta 2. This is a very useful connection, because from a single transistor many times the current gain is not very high, it is 100, 200, maximum 300-400, but this is the product. If we couple this way, we form a Darlington pair out of the two transistors, then gain will be very high. As an example, let beta 1 be 50 and beta 2 be 60, then for the compound this Darlington pair, the current gain will be equal to 50 into 60, which is 3000. Darlington pair which has been formed with two transistors individually having current gain of 50 and 60, when they form a Darlington pair, then the current gain available will be 3000. This has wide applications. It is formed even in integrated circuits, and otherwise also in discrete circuits Darlington pair is widely used. Darlington pair is actually, in reality, these are two emitter followers, with infinite emitter resistance with first transistor. How we can show that this is this? For AC purposes we ground this, otherwise it will be a biasing we will have to provide, and this is what we said, this RE1 is infinitely high and this is the load, this is emitter follower, we are connecting the output from emitter to the next stage, and at the next stage this is Q1, this is Q2, we are taking the output here and we are giving input here with respect to ground, of course. Here also with respect to ground the output is taken, and this is RL. Then since beta is beta 1 by beta 2, now see here there is another advantage, gain, current gain of the Darlington pair is very high, so is the input impedance. What is the impedance here? Impedance here, that is Z I at the second stage. You remember the fundamental thumb rules that for a circuit in which the input is given at base, whether it is common emitter or this common emitter follower, this is equal to the beta into load resistance. Load is here now RL at the emitter, because it is emitter follower, we always connect load at the emitter. So, this will be ZI 2 is equal to the current gain into the load resistance RL. This we have done earlier, and I am sure you understand that this is the beta times the load. So, it is this, and this will act, Z1 will act, this is infinity, this is in parallel with infinity. So, the result will be simply Z12, Zi2. Zi2 is the load for the first stage, because this is infinity resistance and this is in parallel. So, the input impedance at the first stage here, this is equal to the beta of it, beta times the input impedance seen here, which is beta 2 RL, very high input impedance, very high input impedance, beta 1 into beta 2 into RL. In the above example, if RL is 1 kilohertz and this collective beta, which is the product of the two, is 3000. So, from 1 kilohertz it will show a input impedance of 3 megahertz, 3 megahertz, very high impedance. So, sometimes Darlington pairs are used to achieve very high degree, very high magnitudes of input impedance. So, we talked about the RC coupling in details, and the response of a RC coupled amplifier was like this. This is gain versus frequency, and these two cutoff frequencies we defined. In direct coupling there is no limit on this lower cutoff, and hence the frequency response of that direct coupled amplifier is like this, where the upper cutoff of course will be here, but lower cutoff is 0, this is gain. And now, so this is the direct coupling, and the special case of direct coupling we talked Darlington pair, which is the direct coupled two stage transistor and which is sold as a unit. Now finally, very briefly, because we have to talk about transformer, the third coupling, transformer coupling. Transformer coupling is very rarely used and there are few reasons for it. One reason is transformers are bulky, they cannot be integrated, not integrable, and their frequency response in general is poor, and to have a high frequency response the transformer becomes very expensive. So, for frequency response poor, for these three reasons transformer coupling is not used, but few applications still are reserved. For example, often now how the transformer coupling, for example, this is the final stage where this is the primary is connected to the collector, and here directly a load like a speaker is connected. This is transformer coupling, this is transformer and it is used if you open your radio sets, transistor sets, then the speaker you may find connected to a transformer. So, this is transformer coupling in which it can take large currents and hence large signals can be passed through the transformer, and without, and DC will be checked, no DC will propagate in the transformer. So, that is the advantage, but these three disadvantages they restrict the use of transformer coupling, and it is very bulky, they are having much weight as compared to other parts and not integrable. Transformers cannot be integrated like capacitor can be integrated, transistors are of course integrable, and frequency response in general is poor. So, that finishes our module 4.